let's take a step out of the lab and in this section do the mathematical formulation of the problem, where we can reason about what exactly that is. Now, here's another, this is just a fun one. Do people still know this guy? The problem's called the Turnpike problem. And I wanted to at least show where the name comes from. Do you know what Turnpike is? If you've carefully seen it here, it was already in the right. I think it comes another time. Oh, I'll go back briefly. Sorry, it's too late. Wow, okay. Amazing series, fun to watch. Sopranos, about a mafia gangster having regrets, and there was the New Jersey Turnpike. Okay, I'm not gonna show it again. It's essentially a toll road. Yeah. It's a toll road. It's the American name for that. A turnpike is really the gate that people in medieval times had, where maybe someone would charge for letting you on their road that they maintained. And for some reason, it still to this day is used for ordinary highways. Whatever. The problem comes from this name for the roads, because what we'll think about is a toll road. You can have many exits. It's a linear arrangement. It's a one-way highway. It's a little stupid. You can enter the highway at any of the exits. That sounds wrong. Any of the, well, they're still called exits, right? You can get in at any point and you can get out at any exit. And essentially what you pay is proportional to the distance you traveled. Now, suppose someone just tells you they've driven a lot, and they just give you their credit card statement with all the charges from the toll road. Can you work out what distance was there between all the exits and in what arrangement they are on the map? That's why it's called the Turnpike problem. Let me properly explain what the problem is. Compared to the mass spectrometry we've seen, we simplify a few things. First of all, we'll assume all the molecular weights are just integers. And we'll ignore this nasty bit that there's these isotopes where for some things you have slightly different weights, even though they're the same atom or the same element. We assume every breakpoint that you could possibly have. Remember, your protein was this long chain of beads. This long chain of beads, and you imagine you have copies broken in every possible way. I wanted to just draw this picture from before again, but maybe it's good enough you can imagine. So there's one copy where you broke it between those two, and for any other possibility, you get a peak. And we also assume if there's several ways to break the molecule into different pieces so that the sum of their molecular weights are the same, then we know this. Well, you'll see this in the spectrometry spectrum by having a larger peak. But we assume that we can exactly read off how many copies will have that peak. And we'll also assume that nobody spat into our sample and contaminated the whole thing. With that, we can assume our input is a sequence of numbers. That's the beads from here. Each has a different amino acid, so each has a different weight. Okay? That's our input. That's what we, in the end, we want to find this. But for the moment, that's what's given. That's the sequence of numbers. The first thing we'll do is we'll do prefix sums. So we take the sum of the weights from the beginning up to a certain breakpoint. That's just for notation. So S for sums, P for protein or positions, or I guess let's stick with protein, but maybe points. I don't know, it's the distances. And then the key definition is the difference multiset. So that's all the numbers we can get from going from the ith to the jth position in our sequence, and all combinations. But it's sub-words. It's not arbitrary collections of beats. It's what we could get by breaking the molecule in various places. Okay? And it's a multiset because it could be that some of these numbers are the same. So a multiset essentially says you can have several copies of the same number. And we know exactly how many of each. Because we do that, the number of these entries here is fixed. For every pair of position I and j, I get one entry. I'll have some examples for you in a sec. Let's do the examples first. So here's, that's the beats have weight 3, 5, and 1, and 2. Now you can break this up in arbitrary ways, right? So you could have just the 3, or the 3 and the 5, or 1 and 2, and all these possible options. Formally, what we defined was the prefix sums and then take differences, but you could really just work out. We have the 1 from the one molecule that's just beat with weight 1. Then we have a 2 because there's a beat of weight 2, and there's no other way to get a sum of 2. But we have 2 copies of 3 because there's a beat of weight 3, but also the substring of 1 and 2 sums to 3. Okay? And so this is, if you do this for every possible I and j, they go from 0 up to n, where here n is the length here. N would be 4 in this example. And then you sum up exclusive. So, okay, from I to j minus 1, pk. That's the sums that you get. And then 11 is the sum of all 4. Okay. Here's another example, a simpler one. If all the weights are the same, they're all 1s, then you just get, from all possible combinations, you get 5 times the 1 from picking each of the 5 individual elements. Then you have 1, 2, 3, 4 options of getting length 2 by every pair. And you have a few 3s and 2 4s and a single 5 for the sum of all of them. Okay? Question?
Why do we don't have 2 times the number 6 in the first example? Is the order of the...
It's only subwords. Yeah, that's important. That's a good point. So there's a 6 because we have 5, 1. But you cannot take arbitrary subsets. Let's maybe, for this small example, write down all possibilities. I think it doesn't take long. So we have the 3, the 5, the 1, the 2. Then I have 3 plus 5. Nobody can read this. I have 5 plus 1. I have 1 plus 2. Then I have the 3 plus 5 plus 1. 5 plus 1 plus 2. Oh God. And the sum of all. And that's all. Okay? That's why this is, if this were not the case, there would be no way to get back to the sequence of numbers. You need to somehow have some information about the order. But all we've got is these weird partial sums. And then the Turnpike problem is the inverse problem. We're given these multi-sets of differences, and we're supposed to come up with a set so that if you build this difference multi-set, you come out with the input. And so here's an example where this doesn't work. It's not always possible. First of all, the difference multiset has to have a sensible number of entries, otherwise you're immediately out of luck. But here 3 is fine. You get a size 3 difference multiset if you have 2 elements. So just 2 beats. Then we get the differences, take the first beat, take the second beat, and take their sum. And if the difference multiset is supposed to be 3 times the same thing, that's not going to work. Right? Then whatever you put, A and B could be the two numbers, and it'll never work out to that distance subset. So it can't always work. There's a question on this. Are we missing subsets of size 1? So sequences of length 1? That's a nitpick of my definition. They're in there. Let me go. Maybe it wasn't the smartest way to formalize it. It's nice and quick to write. So here we take the difference of two prefix sums. And I'm not allowing I and j to be the same. That would give me a difference of 0. But I'm allowing j to be I plus 1. And so when j is I plus 1, I get essentially one of the pi's. You could also have written immediately just some of these, but then you would somehow need a notation for summing up a substring. I found this smart, but maybe it's more confusing. All it says is what we've done in this example. You have the 4 letters. Now you can take the length 1 substrings, the length 2 substrings, the length 3 substrings, and so on, and always sum up their weights. Okay, the room fell silent. That's the right moment to have you think about a bit. This is the first non-trivial size, right? It's 6 numbers. So n will have to be, I'm looking for 3 beats. Then I can make 6 combinations, 3 length 1 substrings, 2 length 2 substrings, 1 length 3 substring, and that's it. What weights would give me this difference multiset? We're heading for a cliffhanger lecture. I'm gonna postpone the. Yep. So you have the multiset here. So that's that one. Yeah, I think few people started figuring it out, and then one submission somehow got split into 3 answers. I don't know if you can fix it. Because the example is so small, you can essentially solve this one by trial and error almost. We will have to have the length 1 substrings somewhere in there. And there's no way, okay, it's integers to make things even easier, but there has to be some weight 1 beat in the chain. Otherwise, we don't get this 1. And we have a second 1, so there's going to be 2 beats of weight 1. All right, so there's a 1 and another 1. That's part of the ingredients. Now, this 2 here might be the sum of those 2, so maybe they're adjacent. But we have another 2. probably that 2 is another beat. So a guess would be that the 2 are adjacent, and then the 2 is the last one. And then you can work out there's going to be a 3 for these 2 and a 4 for the whole thing, and that actually matches. That wasn't too bad, maybe. Various people found that in the small case here, you can do it by trial and error. But it's kind of hard, right? Yeah. That's true. That's true. Yeah, the whole problem is oblivious to reversing the word. So the best we can possibly hope for is identifying the sequence or its reverse. We cannot distinguish those two. Yep, that's a very good point.